Hi, fellow geochemists and geochemistry enthusiasts. Welcome to GeOCHemISTea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire future geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Scher, and this month we're talking with Scott Halley about trying to mineralogically quantify your rocks from 4-acid geochemistry data. Today we're joined by Scott Halley, a consulting geochemist with over 40 years of experience in mineral exploration. He's the founder of Mineral Mapping, where he works with companies around the world to interpret multi-element geochem and hyperspectral data. He's also well known for his geochem short courses through codes and his practical approach to understanding alteration systems. Scott, one of the goals of geochemistry is to show the younger geoscientists and geochemists what a career in geochemistry can look like. Can you tell us about your journey through the field and what's kept you passionate about it?
That's a long story, Sam.
We got time.
I got into geology when I was a little kid. My grandmother was in the local gemstone club. So weekends she would go out fossicking for petrified wood and agate and cut them up and polish them and stuff like that. My grandmother's brother owned a sheep grazing property and we used to spend our holidays there. And on his property, it was geologically, it was Permian sediments covered with tertiary basalts. And at the base of the basalt flows, there was petrified wood and agates in the interlayer sediments. So we'd wander around the sheep farm, picking up gemstones and filling our pockets all day. And in the area where I lived, there's some really funky alkaline basalts here that have, in places, they have these big red zircon crystals, xenocrystic zircons in basalts. And there's a couple of localities where these things are eroded out and you can go into the creeks and pan and sieve for gem quality zircons. So we used to do stuff like that. Some of the coastal exposures here have these columnar jointed basalts that have massive big mantled xenoliths, the olivine, pyroxene, lertzolites. And even when I was a little kid, I'd go out there with a hammer and a chisel, and I'd spend a whole afternoon smashing these things trying to get the xenoliths out. I've still got a cabinet full of those things in my house now. So I was always going to be a geologist. And then when I got to high school, one of the subjects we had at high school was geology, would you believe, in high school. And the best teacher I ever had in all my time in education was the geology teacher in year 11. And when he was teaching a class, he had a habit of licking his lips constantly. So he was doing this kind of thing. And so his nickname was Snake. So Snake Robinson, who was teaching geology, and you'd start off with the basic igneous sedimentary metamorphic stuff, but his real passion was mineralogy. So even in a year 11 high school class, he had us drawing crystal structures with sketching little silica tetrahedra of island silicates, chain silicates, sheet silicates, all that stuff. I just loved that. It was awesome. It was awesome. Snake Robinson, he was a gun. And so I was always going to be a geologist. And then I went from there to TasUni. I'll tell you some more stories about TasUni. That was a great experience. That was in the days before codes. And then I went to ANU for a PhD, drawing phase diagrams of magnesium fluorosilicate minerals in a tin scale. It turned out to be super useful. Not, but it was good fun. TasUni. When I went to TasUni, it was an amazing place. The head of the department was Professor David Green, who was one of the preeminent experimental petrologists. And in the basement of TasUni back then, they had a high pressure, high temperature machine. They would make up little aliquots of powder of known compositions, and they'd enclose it in a capsule, and they would cook it at a set temperature and pressure for however long, and then see what minerals grew from that. As David Green had an amazing array of PhD and postdoc students working with him. And in the days before codes, the economic geologist at TasUni was Mike Solomon. And Mike was a legend in economic geology. And he had some extraordinary students working with him. He had Jeff Green, who did his PhD and then postdoc on VMS systems. And Tasmania's the land of VMS systems in the Mount Reid volcanics. So Jeff Green was doing his postdoc in Japan on the Kuroko deposits. John Walsh was working on the thermodynamics of chlorite solid solutions. He later became my PhD supervisor. Another guy there was Chris Eastoe. Chris was super interesting. And he became professor of geology in Arizona. But Chris Eastoe was doing his PhD on the Panguna porphyry copper deposit in Bougainville. And I remember going past the fluid inclusion lab one day when I was a little meek and mild third-year geology student, and Chris Eastoe asked me to come and have a look at some stuff in his fluid inclusions. And he had these massive big fluid inclusions with daughter crystals of halite, sylvite, hematite, and chalcopyrite sitting right next door to these great big vapor-rich crystals. So you could see fluid unmixing, preserved in time and space. Just amazing. That was like Christmas. That was the best Christmas ever, seeing these hypersaline fluid inclusions in a porphyry copper system. Just amazing stuff. And going into TasUni as an undergraduate, every day you're walking down the esteemed corridors of the department, bumping into these giants of economic geology. Just amazing experience. My first job was with a company called GeoPico, and they were like a mid-tier Australian gold, copper, VMS mining company. And then I switched to another company called Renison Goldfields Consolidated, that's RGC, but we called it Really Good Company. And RGC had their own in-house group of technical specialists. So they had two structural geologists who were like mapping specialists. They had a really good geophysicist. They had these guys who were working on these weird things called computers. We didn't have computers back then because and they had the world's best geochemist, a guy named Simon Gatehouse. And at that period in time, instrumental neutron activation was just becoming a thing. Right? So we're starting to get these data sets with 20 or more elements with really good quality data. And Simon knew there's a lot of value in this stuff. So he wanted to be able to manipulate multi-element geochem, looking at lots of different components at the same time. So he wrote his own program to do that. And he called his program Geochemical Analysis System, or GAS for short. And later, IO Global took up that bit of software and rewrote it in a sensible logging code, and it became IO Gas. But Simon Gatehouse started doing that stuff in the early 1990s. And I got to look over his shoulder for a while, and that's another great Christmas. That was awesome. So I worked as a exploration geologist for 20 years, just out in the bush, mapping, sampling, drilling holes, logging. And RGC split off its gold assets into a company called Goldfields, the Australian Goldfields, not the South African Goldfields. They merged with another Australian gold miner called Delta, became Orion Gold. And then Orion Gold was taken over by Placer. So I kept the same job, but worked for 4 different companies. And then Placer was taken over by Barrick, and they made me some pretty unattractive offers. So I thought, I'll go and do my own thing. So that's when I started consulting. So 20 years working as an exploration geologist, and then I started consulting. And when I started consulting, people wanted me to look at their geochem data, not do exploration 101. So almost, I don't know, it was a fork in the road whether I continued as a geologist or a geochemist. But having that background in exploration before 100% specializing in chemistry was a really important thing. And if I look back at how I got to this point, I can pick some key people in that progression, like Snake Robinson for sure, Mike Solomon, John Walsh, and Simon Gatehouse, and then Greg Hall. If it wasn't for those people and the chance to work with those people when I was a young, malleable geologist looking for something useful to do in life, I wouldn't have ended up where I am now. So finding people who you find interesting and inspiring and tagging onto them and learning from them is a really important part of the journey.
That's amazing. I couldn't agree more with that. Yeah.
Yeah.
So you're a few years into consulting at this point.
20 years at this point.
How do you keep passionate about it, or what makes you want to keep doing it?
I've seen enough data now that I think I'm learning new things faster now than ever before. As you gain more experience, you also gain the ability to learn. I'll look at a new data set, and more often than not, it'll be something that I've seen 50 times before. And I think I can see pretty much what's going on within the first half hour. But when I find things that are not like anything I've seen before, like they really jump out. And I find that really interesting, just recognizing the oddball things, but recognizing the same pattern over and over in different places. Like you one thing once and it's interesting. You see the same thing twice and you get curious. You see the same thing 3, 4, 5 times and it's important. And recognizing, making those connections, you have no chance of making those connections until you've seen lots of data and lots of different systems. So as I get to see more and more things now, I can learn faster and faster. And that's just a real buzz.
I love that. So you just won't stop because you're just like, I just need to understand more for my own personal pleasure. I kind of love that.
Yeah, it's all about, it's fun. It's like playing computer games in a way. But when I look back at things I've done in the past, like I have done some really dumb shit. I've written some awful reports. Every time you see some geochem data, there's always some degree of ambiguity in there, right? Unless you go back and look at the rocks and say it could be this or it could be that, chances are you're going to get something wrong. And I know there's things I've done in the past that I got wrong because I just didn't have enough experience to recognize what was going on. And I don't make as many of those mistakes now, but I still do make mistakes for sure. And like it always makes me laugh when you see brash young kids coming up and saying blah, blah, blah. And you think, mate, you've got no idea. Yeah, but it shouldn't discourage people. But yeah, we do get things wrong. And early in our careers, we're not smart enough to know that there are multiple hypotheses that need to be tested.
I think that's a nice way to put it, in the sense that I think there's so much ambiguity regardless in geology. We're never going to necessarily get it 100%, but just going into it with the fact that you can't just go into every porphyry deposit saying that I know this because I've seen it or somebody's written it and therefore this is the rule, and then going in and seeing a data set and refusing to think there actually could be 5 different things that could be going on here.
No two porphyry deposits are the same. They are all different.
Yeah. I find it interesting with the porphyry. I didn't mean to bring up any dirt here, but I find it interesting the porphyry because I feel it's alleged to be the best understood of them all, the one that has just the strongest models out there. But really, I've seen a lot too between geochem and hyperspectral data, and I haven't seen nearly the amount that you have, but I've seen enough to where it's just like what we think we know necessarily isn't true. And also, again, they're all so different. It's almost alarming that we lump them in, that they should all have the same model. So,
yeah. There's a name for that, Sam. It's called cognitive entrenchment.
please
Right?
do tell.
We go into something believing that there's some kind of truth that isn't really there at all. So, like porphyry's classic example, we log potassic alteration, right? But the dominant reaction that happens in a porphyry system is plagioclase plus sulfur dioxide equals albite plus anhydrite. You know that porphyry copper magmas do not fractionate the sodic end of plagioclase, so they are sodium-rich magmas. So the fluids that exalt from them are sodium-rich. And when you look at the chemistry in the potassic zones, there's always twice as much albite as there is orthoclase. If you were classifying the alteration types based on the composition of the rocks, you wouldn't call it potassic alteration, you'd call it sodic alteration.
But then one would argue, number one, the rocks are pink, and number two, if you have sodic addition, then you must be in a propylitic zone.
And usually there is not that much a loss or addition of sodium and potassium. The dominant effect is addition of sulfur. Yeah, just look at the assays of the rock, what is actually in there.
But it's pink.
There's just because it's pink doesn't mean it's orthoclase.
It's
There's
interesting
just as
when
much
you
pink albite as there is pink case bar.
It's interesting when you do the feldspar staining and then it actually comes out, even though it's pink, it's not actually potassic feldspar.
There's orthoclase in there, but there's twice as much, on average, there's twice as much albite as there is orthoclase.
Yeah.
Interesting. But like, we know we're in the middle of the copper grade shell, so by definition, it has to be potassic alteration. Like, we're just giving it a name, but we're not actually saying what's in the rock.
Yeah. And I find it interesting too that, especially I think a lot of people that are more peripheral to porphyry, they haven't really worked in it before, because I know a lot of very good porphyry geologists, and I don't want to be shaming anybody here. But I think there's a lot of misinformation too around how much grade can be carried in the quote, if we will, phyllic zone of porphyries as well. So there's just this bizarre amount of good information, but also, if I care to say, misinformation circulating around too.
Yep.
Yeah. Yeah. Wow. I think that was a little bit kind of tea-ish.
I think so.
Yeah. But that said, we want some actual tea, because now we're going to say it's officially tea time. So what have you brought for us? We're so ready for you to spill.
Why don't we jump into a discussion on the paper? Or is that breaking the rules?
This is breaking the rules. A little small story. Don't kill it.
Okay, I'll make up another story.
I love it.
I'll tell you about my best day ever as a geologist.
This is perfect.
I think it would have been, what year? It would have been 1992. I was working on a project in Western Tasmania. We had, the rocks down there was really weird. We had a little gold project called Henty Gold Mine. Well, it wasn't a mine then, it was just a prospect. And at the time, we thought this thing was a modified gold-rich VMS system. It had sphalerite and galena. It was in the Mount Reed volcanics. It sat on the same stratigraphic position as known exhalative VMS systems, but the copper, lead, zinc values were 0.5%, 1 or 2%, not that much. But it had this amazing silicified zone in the center. This rock was like 95 to 98% silica. It was
Wow.
massive silica. And in places it had a peripheral porphyry, fluorite, topaz, and then zoned out into a quartz mica rock. Anyway, we drilled a bunch of holes into this, and you drill one hole and you get a couple of meters at 30, 40 grams, and you drill the next hole and get not much. And it was teetering on the edge if it was going to be an economic deposit or not. I remember there was one Friday afternoon, and it was quite late in the afternoon, so everybody had knocked off, but I was still in the core shed, and the field assistants had just driven out to the site to pick up core and bring it back to the shed before they knocked off for the weekend. So they came in and they had 50 meters of core, and we laid it out on the logging racks, and we drilled through this quartz zone, and it was 12 meters of quartz with pyrite and a bit of base metal sulfide, and every stick of core had coarse visible gold in it.
Whoa.
And the intersection, and the drill hole number was HP 96. So the ore zone ended up being known as zone 96. And the intersection came back at 12 meters at 107 grams per tonne. So that was beer o'clock, 6 p.m. on a Friday afternoon in Queenstown, on the west coast of Tasmania. That was just the most exciting day ever in my geology career.
Did you get to keep a piece of the core?
No, but I got a chunk of rock full of VG that came from the first heading that had driven into the ore zone.
Ah, love that.
Yeah, that's very cool.
Well,
Like we
yeah.
spend our whole careers just hanging out for a day like that. Yep.
I'm pretty stunned. That's so cool.
Yep.
Wow.
The best discovery I ever made, or that I ever had a direct involvement in, was an extension of that Henty project. Like we closed off zone 96 and drilled through another dead zone. We thought, oh, that's the end of the ore body. And then I spent like another 6 months just re-logging all the old drill holes and mapping on the surface. And there's a canal had been cut through that part of the stratigraphy as part of a hydroelectric scheme. So I was mapping the rock cuttings in this canal in the middle of winter. It was piercing down with rain. There's chunks of ice and snow floating down the canal, and I was wading around the margins, logging this stuff. And we realised that we hadn't actually closed off the system. So the best discovery I ever made was the extension of that thing. And that was found with zero geophysics, zero geochemistry, just mapping and logging. And the extension of the ore body was an ore chute that was in the footwall of a thrust fault. So it had no surface expression. We were just drilling down parallel to the fault to intersect this ore zone. And we were drilling like 1,000-meter holes. And we found the big ore body, like that turned out to be 1 million ounces.
Wow.
No geophysics, no geochemistry, just look at the rocks.
Just mapping.
Yeah.
Love that. For all the geologists that listen to the podcast. All right. So let's now chat about what we wanted to chat about here today, which was that every geochemist, or many at least, have wrestled with a spreadsheet at least at some point in their lives, but few have really turned one into a modeling tool that's lasted any length of time. So with that, I guess we both want to talk about what you've been up to lately, but also first chatting about kind of the work that it's based on. So if we first want to start with the Herman and Barry, what was it? 2001, 2002, 2001 paper, where they were originally trying to solve mineralogy using what they called MINSQ in Excel. So can you start us off with just an explanation of kind of the basis here of where we started?
Sure. We'll go right back to the very beginning. Every time I get a new job looking at geochem data, the first thing I do is to merge the assay table with the logging observations. Merge the logged lithology and the logged alteration codes from the geologist with the assays. And then we'll make a series of alteration diagrams. So we'll do the potassium, aluminium versus sodium, aluminium, molar ratios, blah, blah, blah. The aluminium, magnesium, potassium ternary diagrams. We know the compositions of minerals. So you know that minerals are combinations of elements in particular ratios. So you can put mineral nodes on all those diagrams. And when you look at the data clouds of the assay points on those diagrams, trends in the data that are running towards particular mineralogical nodes. Right? So you can pick what the mineralogy is going to be, you can pick categories, but it's not quantitative. And what we realize is when you do that, in nearly every case, you could not just take the logged alteration that the geologists have observed and make a reliable mineralogy model out of it. Like, we just cannot pick the minerals consistently enough, and we certainly cannot pick the quantities of minerals. So that was the rationale for Wally Herman and Ron Berry making that initial MINSQ program. That started out because back then, in the late 1990s, Codes was making an atlas of alteration types in the Mount Read volcanics, and Wally was running the project. So Wally was getting thin section work done. He was describing the thin sections. He's putting in whole rock analyses. He was putting in spectral data and describing the classic types of alteration in these VMS systems. And he realized that none of the chemistry he was putting, none of the mineralogy he was putting there was quantitative. It was all just descriptive. So he sat down with Ron's a genius. Ron is a structural geologist, but back then he was probably the best mineralogist and best chemist in the Codes setup. And he solved mathematical problems in his spare time for recreation, just because it was fun. So Ron said, look, we've got this solver plug-in for Excel, and it can do mass balance calculations. So if we know the mineralogy, if we know what minerals are present in the rock, we can do a mass balance calculation and turn it into calculated percentages of minerals. So that's how it started. It was a much better option than doing point counting on a thin section. And it was way cheaper than doing quantitative XRD, which is just starting to kick off back then. So it's just turning assays into percentages of minerals. So that was the starting point. The limitation of the MINSQ method was that if you'd measured the number of minerals you could calculate was one less than the number of constraints. Right? To make that algorithm work, if you'd measured 9 major elements, you could only calculate 8 minerals, which meant that you could not pull apart solid solution chemistry. Right, so you would have to put in a fixed composition for plagioclase. You'd have to put in a fixed composition for the white mica, a fixed composition for the chlorite, in order to reduce the number of things you had to calculate with that method. So that was the 2001 version. And then Ron thought, it doesn't give us enough flexibility to calculate all the things we need to calculate. So I'll try a different algorithm in that solver suite of things that come with Excel. So then he went to linear programming. And linear programming allowed you to put in far more variables, but you needed to set some kind of probability of different mineral phases being present in the sample. You get an infinite number of possible solutions when you go to linear programming because you've got more variables than constraints. So how do you decide which one of those infinite solutions is the best solution? So this is an optimization method. And the first kind of optimization method that they came up with was just to select probabilities or input probabilities and just keep tweaking it until you got something that looked about right. So that's you would have seen that probably written up by Angela Escom in her paper on Productora.
I did see that. Yeah.
Yeah, and that was really good. Yeah, so that's we've not randomly, we've picked probabilities for white micas versus feldspars versus something else, and it looks like we're underestimating white micas, so we'll just tweak the dials and turn up the probability of forming white mica. And it looks about right. So that's just trial and error. You could constrain that to some extent by having a training data set of quantitative XRD. And then Ron had the idea of, instead of randomly putting in probabilities, let's use a Gibbs free energy value as a constraint.
Can you quickly just describe what Gibbs free energy values are?
Yeah, basically everything rolls downhill till you get to the bottom of the hill. Gibbs free energy is a thermodynamic constraint that every chemical system will react until it reaches a point of lowest contained energy. So if you mix a bunch of elements together under certain pressure and temperature conditions and allow it to react to completion, that will predict what the equilibrium mineral assemblage is going to be. And it's a function of temperature and pressure and water content, but dominantly temperature controlled. So for example, like if we just dumb it right down, hydrothermal systems that run at temperatures less than 350 degrees will make white micas. Once you get above 350 degrees, you're likely to make black mica, you're likely to make biotite in preference to white mica. If you've got a well-constrained data set, then the thermodynamic properties, like specifically the Gibbs free energy, is likely to predict that for you. Yeah?
Yeah.
Like a really simplistic way of thinking about that is in metamorphic petrology. You can have exactly the same rock composition, but as you ramp up the metamorphic conditions, you'll go from night pumpelite to lower green schist to middle green schist to upper green schist to lower amphibolite and so on. You'll make completely different mineral assemblages with the same rock composition. So the Gibbs free energy constraints in the linear programming method are just a way of predicting how that mineralogy changes with temperature. One of the really good examples of that would be Corbett and Leach. Remember their temperature pH diagram they
I
had?
do. Yeah, it lives in my
Like
head.
that is an absolute cracker. So the Gibbs free energy constraint is just a way of mathematically replicating the Corbett and Leach diagram.
Yeah, and for anybody that doesn't know, it tries to, I can let you describe it if you want. Please, you're the guest. I'm the host.
Okay, so the Corbett and Leach diagram, they have drawn a matrix where they'll plot temperature against acidity. So they'll go in increments of temperature and increments of pH and describe the mineral assemblages that you would see with those particular conditions. And it's diagram, it's schematic, but it just shows how the relative proportions of feldspars versus micas versus aluminosilicates varies as a function of pressure and as a function of pH and temperature.
So many
If you
great
haven't got
things.
it, if you're a
Yeah.
young geologist listening to this, you should look up the Corbett and Leach temperature pH diagram. It's fantastic.
Yeah, I had that in my field notebook for logging, to be honest. And it just stuck with me through there. There's a few, for the young geos listening, there's a few key diagrams out there that whether or not you are afraid of geochem or embrace it, there's some really great schematics made out there like Corbin and Leach that will just help you while logging to understand how things are changing and perhaps why you're seeing certain things in the core based on different mineral assemblages. And I found that to be one of my diagrams that was super helpful.
Yep. Yeah, so the Ron Berry calculated mineralogy version, so you got to the linear programming thing.
Yeah.
With probabilities based on thermodynamics. And that's Ron had just come up with that version when I moved back to Tasmania like 7 years ago, and I started getting involved in things that were going on at Codes. So that's about the time I turned up at Tas Uni. And on my C drive, I would have the drill hole databases from probably, I don't know, probably 200 different operating mines around the world. So I was plugging all of those into the Ron Berry program and running them. And some of them worked okay and some didn't. So when we got things that didn't work, we tried manually changing the Gibbs values we put in there until we got a better outcome. And sometimes it worked okay. It worked to a degree, but it was never ideal. And because we were tweaking the dials until we got something that looked better, it meant that the results we were getting were operator dependent. Like everybody could try it, but would all get a different answer. And that's not satisfactory. It's not repeatable. And then I realized that the main issue with that wasn't the thermodynamic constraints. The main issue was actually the way we were dealing with solid solution chemistry. The biggest problem was that to run that program, you'd have to put in assumed compositions of minerals, and you'd have to put in like an average for the whole of the deposit. And Sam, you know very well how variable the white mica compositions are across a deposit. You know how variable the chlorites are. You know how variable the plagioclase is. You can't just put in one composition for those minerals for the whole of the deposit, an average, and run it. Like it's just, the error bars are going to be huge.
To illustrate this, guys, working so much in core imaging with hyperspectral, you would see over the course of pixels at the size of 500 micron, 250 micron, you would see changes in chemistry of these minerals. So, uh, yes,
Yeah. So
there you go.
if you think about the composition of white mica, we would write a theoretical end member for muscovite as K, Al3, Si3, O10, 2OHs, right? But it's never that. The potassium number is always less than 1, and there'll be iron and magnesium substituting for aluminium, and it's a coupled substitution. As you put iron and magnesium in, then you got to put in more silica in place of the tetrahedral aluminium to balance the charge. So really, the white mica is going to be potassium, Fe2 plus, Fe3 plus, Mg, Al, Si atoms per formula unit, and they all vary. They don't vary independently because they're coupled substitutions, but you've got to be able to, if you really want to be able to do the mass balance calculations properly, you've got to be able to put in a realistic estimate for the mica composition, for the chloride composition, and for the plagioclase composition, and vary it sample by sample to minimize the errors in the mass balance calculations. So what I've been doing in the last 2, 3, 4 years is writing little subroutines that predict those solid solution variations on a sample by sample basis, just by looking at various cation balances. And it's not perfect, but it's way better than it was. And when we're doing it in the Excel-based version, it was painfully slow to run. Like it would run really slowly, and you'd run the whole thing and the answer wasn't quite what you wanted, and you thought, oh, I can do this better, and you'd tweak the dials on compositions or Gibbs values and then run it again. And some of the PhD students at Codes who were doing these doing this stuff as part of their projects, they were doing these mass balance calculations for months and months, like literally, until they got a result that was okay. To be able to do this thing properly, we needed to take it out of Excel. We need to put it into a different programming language that ran faster. And we needed some smarts in there where we could vary the mineral compositions on a sample by sample basis. The other really important thing is that we can put in hypothetical N members for solid solution variations, but how does that compare with reality? So we would write chlorite as FeMg5 Al2 Si3 O10 1008 OHs, right? But the aluminium number in real chlorides is never 2. It's almost always significantly more than 2. So we've spent a lot of time looking up published results for mineral chemistry to see what the natural ranges of atoms per formula unit are likely to be in all the biotides, the chlorides, the micas, etc. And we've captured that in the new code. We know what the 90% of all chlorides will have this range, 90% of all micas will have this range. And that varies as a function of temperature as well. So we've set those boundaries into the code that allow for those variations in mineral chemistry. So what we're trying to do with the program I'm working on now is that it will have a user interface where you can load up your CSV data. We've got to set a mineral matrix. So you need to have a list of minerals that are present in the system and break down those minerals into the constituent elements. So you convert from atoms per formula unit to percentages of elements. You've got to put in an estimated temperature so that it kind of matches that Corbett and Leach kind of diagram that tells you what the illite component in the micas is going to be, blah, 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 that kind of stuff. And it sets a list of likely minerals that you're going to have in the system. You get a much better result if you have some independent information about what minerals truly are in there. So you got a tick list. You can add or remove chlorides or biotides or amphiboles, etc. And then you run the program and then you validate it. So the validation.
I was just gonna say, what would you do? So just throwing out numbers here, your porphyry system forms at, this is wrong, 700 degrees C, right?
Yeah.
But we know that there's a lot of examples of porphyry deposits out there that have late stage overprints of different types of clays. So how would the program account for that temperature drop? Because we're going to see then the primary mineralogy, but would we see the illites and the kaolinites and the montmorillonites as well?
That's a weakness of the linear programming method. There are some mixtures of minerals that are just not solvable. So if you, in multi-dimensional space, if you have 3 minerals that plot on a line, you can solve for 2 of those minerals, but not 3. So, for example, we could solve, if you had kaolinite, white mica, and orthoclase, you can solve for any 2 of those, but not 3 of them.
Interesting.
If you had bornite, chalcopyrite, and pyrite, you could solve for a mixture of chalcopyrite and pyrite, or bornite and pyrite, but you can't solve for bornite plus chalcopyrite plus pyrite. So there's a limitation to what you can do. Sometimes the overprinting is distinctive enough that it works out okay, and sometimes it doesn't. So that is definitely a limitation. What I try to do is I would try to optimize this for the stuff that dominates in the ore zones. So if I get things wrong in the probabilitic zone, I don't give a rat's ass. I try to get the best possible fit to the mineralogy that I know is present within the grade shells. But it's still just an estimation technique.
I guess it's one of those examples too, where it's a powerful tool as geochemistry is to begin with, but then you can only improve it with coupling other things with it that would give you the complementary things that if you're observing different clays or you have questions about different clays, then using a different tech to perhaps supplement that and answer those additional questions would then be helpful.
That's exactly right. I guess the problem is that logging core in a quantitative way, like we just can't do it. It's just too hard. So we're looking for some way of estimating quantitative mineralogy. And the first measured data set we ever get back on a drill project is the assay data. So this is the first model that you would make. And the way our program's running now, once you get your assays back from the lab, I can turn this into a 3D visualization of the mineralogy literally in 15 minutes.
Yeah, that's wicked.
But this is the stuff you would do before you go and spend extra money collecting extra data sets. It allows you then to be smarter about where you would go and select samples for more detailed studies. If you had another data set that you could add into this, you wouldn't have to use that probabilistic model to do the calculations, right? If you know exactly what minerals are in each sample, you can use completely different math to solve it, and you get a much more robust result. But this is just like the first pass that you would do before you spend money on extra data.
And so talking about extra data and then also just mineral formulas too. What do you do then? So a lot of our minerals we're talking about are silicates. We don't get silica. What if you're working in a deposit that has a lot of carbonate, so we don't get carbon? And then importantly too, we also don't have loss on ignition or kind of like water data. So is this something that you think is there would be a different iteration of the program if you had all of that information? Or are we just saying, hey, in industry, we have to do with what we got. We get 4 asset data routinely. And this is one of those solutions that's really getting towards maybe even better than an 80/20, which is more than you can ask for in industry, I think.
Yep. A sad reality is that there's no assay method that gives you everything you want.
Nobody's going to pay for that.
Yeah, like I could spend a whole afternoon talking about what you're going to get from your assay data. But first and foremost, we analyze rocks because we want to know the copper grade, the sulfur content, the moly, blah, blah, blah. So the best fit for purpose method that gives us what we primarily need is ICP. And we don't get silica, we don't get carbon, we don't get loss on ignition. The program we're writing you can put in all those other things, right? If you've got them, you put them in. If you haven't got them, then you work around it. What we do put in, like the bare minimum you need to do this is the majors that you get from 4-acid digest. So you get aluminium, calcium, iron, potassium, magnesium, sodium, titanium sulfur. Like that'd be the minimum suite you'd have to put in to make it work. And then we have another column, which is the sum of everything that you haven't analyzed. Right? Rest includes silicon, oxygen, water, blah, blah, blah. So we're treating rest like it's one of the components of the mineral phase. And when you do the mass balance calculation, you're going to assign all the aluminium, all the iron, blah, 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 into mineral percentages, and you have a big amount of mass left over, and that will be almost all quartz. And it turns out, surprisingly, that the quartz estimates are really accurate. Like the error bars on the quartz estimate is way smaller than what I ever expected. I'm really surprised about that. Carbonates are a bit of a problem, but we know that The plagioclase composition is predictable depending on what the host rock is, what the plagioclase is going to be in basalt relative to andesite relative to dacite. So knowing the composition of the rock pretty much sets the likely calcium-sodium ratio in the plagioclase. If you have a calcium-sodium ratio that's higher than that, it'll force the program to assign that calcium to a non-silicate phase. Yeah, it's not perfect, but by being smart about the guidelines you put in for feldspars in here, you can get an okay estimate of carbonates. You'd have to see it in action to know what I'm talking about. But
Yeah.
You can't just say, oh, I've got albite and I've got anorthite, because then it's going to put all of the calcium into plagioclase and it's going to be rubbish.
Right.
There's a limit to how much calcium will be in plagioclase, depending on what the host rock is. So there's like a squillion little things like that that are captured in the program.
This is really fun. Who do you think that this is going to be useful for? Who would you recommend the user for? Do you think that this could be really something that any geologist could use?
Good question, Sam.
I have all the good questions.
It's taken me 20 years to learn how to do this.
Well,
Right?
that's
So
the point, right?
it's
And I've
taken me 20 years to learn how to do it. When I set it up with the Gibbs values and I've run test after test, what I found was that there's a couple of the Gibbs values that I would routinely change a bit to get an answer that was a better fit to the data. So the way I fit it to the data is that I'll make the alteration diagrams and I will color those diagrams by estimated percentages of minerals, so that as you approach a mineral node on one of those diagrams, you should see the percentage of that mineral progressively increasing towards that node. Right? So I can see when I've got a plausible result. I don't know that it's right, but I can tell that it's plausible. So to get a really good plausible result, there's a couple of the mineral Gibbs values, probability values, that I always had to change by about the same amount. So I think maybe the thermo properties that we're using are not brilliant. But if I hardwire that change in the Gibbs values into the program, I've got to the point now where I can load the data and run it and get a result that looks plausible without having to do any manual intervention and tweaking of the dials. So what that means now is that anybody can load their data and replicate what it took me 20 years to learn in about 5 minutes. The whole idea is to make myself unemployed, to replace, I'm just trying to write a program that captures the things in my skull that I don't have to do it anymore. Yeah,
I
so
love that.
that's the end goal, is to set this up so that anybody can do it. Everybody gets the same result and it doesn't need any expert intervention. And it's still just the first model you'll make, but and the numbers might be wrong, but the relative values are still meaningful. So once you put your kind of grade shells inside of this, you can see the variability of the gangue components. You can start domaining the ore resource models by variations in gangue mineralogy.
Super fun. Do I have any other questions? I'm not sure. Is there anything
I'll
else that
tell
you want
you,
to say? Tell me.
yeah, I'll tell you why I started doing this.
You want to retire.
No, how I got involved in this. I was approached by some guys to do the old Excel version of a calculated mineralogy model on a project they were working on. They said, oh, we got 60 drill holes. Can you run this through your program? Yeah, okay. So he did that, and I sent the results back to him. It turned out these guys were a geophysics company, and they specialized in 3D seismic. This is HiSeis. It's an Australian 3D hard rock seismic company. And they had 3 holes where they'd done wireline logging. And when they plotted the mineralogy against acoustic impedance measured in the drill holes, they found there's a straight line correlation. And they said, your beauty, we've got wireline logging on 3 holes, but we can use all 60 holes where we have chemistry to constrain the way we do the 3D modeling of the seismic. And I said, for hard rock seismic, this is a game changer. And then they came back to me and said, would you like to commercialize this stuff? And at that point, I was doing all this in Excel, and I couldn't do this row by row changing of the mineral chemistry because I didn't know how to program it. But it met my need because they could do the programming that I couldn't do. And it met their need because then they could use chemistry to do a constrained inversion of geophysics. So we started doing that, and then it all went quiet. And I discovered that High Size was being bought out by another geophysics company called Fleet Space Technologies. And Fleet Space Technologies do lots of really funky stuff. They build satellites and all sorts of things. But they were also doing lots of passive seismic, and they needed to extend into active seismic. So they bought out High Size, and they've been resourcing this to make the program and get a really schmick user interface. And it's maybe a month away from being finished. So that's how come I got to be doing a geochemistry project with a geophysical company. The other thing that calculates now, in the geophysics literature, there are lots of measured physical properties of minerals. So we know density, obviously. We've got a proxy for hardness called Mohs scale, everyone knows about. But we've also measured bulk modulus, shear modulus, P wave velocities, S wave velocities of minerals. So in the back end, once we've calculated mineral percentages, it also does a weighted estimation of P wave, S wave, density, blah, 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 and it back calculates whole rock SiO2. So what these guys are going to do is that they're going to continue doing their kind of 3D seismic models. They'll have predicted velocities in 3D space, but they'll start using downhole chemistry to do constrained inversions of geophysics. And how exciting is that?
The irony.
We're working in silos where, like there's geochemists over here and there's geophysicists over here and there's this massive gulf in between. And now we're going to join them together. This is awesome.
I love that. Just from the sense that eventually I feel that all my geophysicist friends, I'm going to have to inform them that they're going to become geochemists too.
Yeah, just hand this to me, fella, and I'll tell you the truth.
Oh my God. Is that us finally winning? No, we're coming together, but we're also winning.
The biggest weakness in our industry now is that we all work in silos.
Yeah.
Yeah. Once we start joining different layers of data together, as we're going to do with machine learning, like our science is going to take off. It's just we're going to get so much better at doing stuff when you learn how to merge different layers of data properly.
I couldn't agree more. Scott, this has been a journey. I love it.
Isn't it good?
It's been so fun.
It's a family trait, like my family. Once we get excited by something, we can't shut up. We just keep talking.
It's perfect. I would ask anybody that's listening to give a thumbs up to this episode if they were impressed by how much I did not talk.
Oh, sorry.
Because I love talking. No, it's a good thing. I think it's a good thing. I'm not supposed to talk that much, but I find that when I get excited about things, the words just keep flying, as do the hand gestures. But because there's no video on these, thank God, nobody can see the hand gestures. But I was so glad to hear all of this, and it was just so interesting to see where this started and where it's going. particularly the irony of it winding up in really in the geophysics realm, them seeing worth in understanding mineralogy and starting from geochem. So I think that this is all really, I think it started in a cool place and I think it ended on a really high note for me at least.
Yeah, good. Yep.
Look, I want to thank you for being here, Scott, and I hope that you enjoyed talking about all this as much as I liked listening to you, and I hope that everybody else did too. I want to thank everybody for listening to GeoChemISTea, and a big thanks to Scott Halley for being on the show, dishing some tea, and talking about extracting mineralogical information out of your four acid data. I want to thank our sponsor, LKI Consulting, and to It's Water and Coma Media for our music, and I'm looking forward to chatting with everybody next month.
Beauty. Thank you, Sam.